Now let us discuss some important points regarding Coulomb's law. So first is, it is applicable only for point charges. You cannot apply Coulomb's law if you have any other shape. Later we will learn that it is applicable if the shape is spherical and that is uniform sphere, then also Coulomb's law can be applied. But as of now, for non-uniform object, we cannot apply Coulomb's law. It is only valid for point charges. Next is, this force is conservative in nature. If it is conservative in nature, what does that mean? Energy will be conserved and hence we can apply energy conservation given that this electrostatic force which we found using Coulomb's law is the present. Now, the direction of force is always along the line joining the point charges. So, if these are two like charges, then they will repel out each other. So direction of these forces is away from the line joining them. And if these two are unlike charges, then they will attract each other. Again, the direction of these forces is along the line joining them. So direction of these forces is always along the line joining them. It might be away or it might be towards each other. That depends on the nature of the charges. Next is Coulomb's law in vector form. So let us say that we have two charges. The Q1 is kept at R1 vector. The R1 is the position vector for this point where Q1 is kept. Similarly, R2 is the position vector of this point where Q2 is kept. If this point is X1, Y1 and Z1, these are the coordinates of the point where Q1 is kept, then R1 can be written as the position vector of point where Q1 is kept can be written as X1 I cap plus Y1 J cap plus Z1 K cap. Similarly, if the coordinate of this point where Q2 is kept is X2, Y2, Z2, then the position vector R2 can be written as X2 I cap plus Y2 J cap plus Z2 K cap. So this is how we can represent our R1 vector and R2 vector. Now, when we need to find the force on Q1, I am calling the force on Q1 due to Q2 as F12. So this is F12. First, let us find the magnitude. What is the magnitude? Coulomb's law said that magnitude is K Q1 Q2 by R square. But which R? The distance between them. So I am treating this vector as R vector. And now I will say divide by R vector, magnitude of that and whole square. So this is the magnitude of force 1, 2. What about the direction? If I add the direction with this magnitude, then this will come in its vector form. So to make it a vector, I am just adding the direction. For direction, I am simply adding the direction. For I am adding R cap. So I am adding R cap vector. So R cap is the direction, this direction. Here I am assuming that both the charges are positive. Hence force will be repulsive. So what is R cap? R cap is nothing but R vector divided by magnitude of R vector. So this is when you write it over here, this becomes cube and this becomes R vector. So now this is cube and this is R vector. And R vector. Now I need to find R vector. What is R vector? See, think about this triangle. So this is my R1 vector. This is my R2 vector and this is my R vector. So I can say this vector plus this vector gives me that. So R2 vector plus R vector gives me R1 vector, and eventually R vector is nothing but R1 vector minus R2 vector. And when we put the value of R over here and here, then we can get this formula which is the vector form of Coulomb's law. So force on one due to other, this is nothing but K, Q1, Q2, and this is R vector cube and this is R vector which is R1 minus R2 vector. So this is the vector form of Coulomb law. Now if we talk that similarly, if we want to write the force on 2 due to 1, which is this. So here I have to use this vector, and that vector is what? That vector is negative of previously used R vector, and which is R2 vector minus R1 vector. So only this vector will come instead of, this is our negative R vector. So instead of R vector or R1 minus R2, now this will be replaced and we will get force on 2 due to 1. So we can write that force on 2 due to 1 is K Q1, Q2 by R cube and times R vector. R vector this time is this vector which is R2 minus R1 vector. Here, if we say that Q1 and Q2, they need to be kept with sign, we already assume that they are positive. So if you put positive and positive, suppose both the charges are positive, they are like charges, so both are positive, their product will be positive and hence direction will automatically be same as what we have assumed. What if one charge is positive and other is negative? So here the product is going to be Q1 into Q2 is going to be negative if they are of opposite sign. One is positive and one is negative. And this negative will also be included over here, which will automatically reverses the direction of F21 and F12. So it will be proper. It will directly give you the force in its vector form. And what if both are negative and negative? So if both are negative, then basically Q1, Q2 will again be positive and direction will be same as the direction which we have already found. So they will like repel each other. So you always need to remember that Q1 and Q2 in vector form, you need to put them with sign. Put Q1 with sign and put Q2 with sign. Now let us discuss principle of superposition. So here, what does principle of superposition says? So as per the principle of superposition, electrical force exerted on one charge due to other charge remains unaffected by the presence or absence of the other charges. So let us say that this is the charge Q and force due to charge 1 will be F1, and we can write, if this distance is R1, then I can directly write magnitude of F1 is nothing but K Q1 Q2, which is simply Q divided by the distance square. I am just writing magnitude. This is not the vector form. I am just writing magnitude of this force. Now whether this Q3 or Q2, they are present or absent, this force is not going to change. How can we utilize this fact? If you want to utilize this fact, then we can say, if I want to get the net force on this small q, then I can find all the forces due to individually other charges on it, which is F1 due to Q1, F2 due to Q2 and F3 due to Q3. So, and I can do the vector addition of all the charges. Once I want to get the net force, then I can simply say that net force on small q is the vector addition of 1, 2 and 3. If there are more charges present, get the force exerted due to that individual charge and just do the vector addition. That gives us the net force on this charge. So we can say the net force, net electrostatic force on any one charge is the vector sum of all the forces exerted on it due to each of the other charges.